Will Stevens, and today I'm going to be going over our fifth lab where I'm going to look at the motion of a falling slinky. So, in this lab, we're going to observe how Newton's second law, plays out in a system at equilibrium and non-equilibrium. We're going to observe the conservation of energy and non-changing forces experienced by this falling slinky. And then our main results is that the bottom of the slinky is going to experience a upward tension force equal to its gravitational weight until the top of the slinky reaches the bottom and then continues to fall downwards. So Newton's second law is force equals mass times acceleration. And from that, we can derive the position and update formulas as we've used in past labs, which we will use to show the motion of the slinky in our computational model later. And then our tension force, in this case where it is an object being hung by not a string in this case, but an upward force, which is our tension, because it is in equilibrium until the top reaches the bottom, we're going to say that tension is equal to the gravitational force, which is mg. So this is what the data looks like. On the left, we have the slinky stretched out before it is dropped in the very terrible GIF on the right. And in this case, the system for this experiment, we are looking at the bottom of the slinky, not the top, not the whole thing, but the bottom. Meaning that the surroundings is the rest of the slinky, the air, the earth, everything else. So when we track the bottom of the slinky, we get this graph where the top hits the bottom of the slinky at 6.5 seconds, and then the slinky goes off screen at the 7.3 seconds where it jumps up, meaning that the rest of the data is irrelevant. So let's set up a computational model to see what it looks like in this. So first we're going to set up our visuals and our other initial conditions with the mass that I found this slinky on Amazon and used that mass. And then I set the bottom of the slinky to the origin, and then we set the net force is equal to the tension plus the gravity. And then we do a first while loop until the time of the top reaches the bottom, and then we recalculate the net force, which is the same thing, and then we do our position and velocity updates, and then update the graphs, and then we do a second while loop from the time at which the bottom starts to fall, or rather the top hits the bottom and then continues on off the screen, where we do the same thing, but we add a drag force now, because that tension force has gone to zero because there's nothing holding up the bottom of the slinky, because they're now together. So when we run that, we get this graph, meaning that the bottom of the slinky does not move until the top of it reaches it, and then it falls together after that time. When we graph the two, we get this graph, where our observed is similar to our expected, especially after the top of the slinky hits the bottom, where they start to both decrease, and you can see the slope there is pretty similar. But we have this upward motion of the observed, which is kind of strange. So, some possible errors. The first is that the point at which tracker was using is pretty variable. Sometimes, especially when something's at rest, it's looking for motion, so it may have accounted for some of that perturbation. But the main one is that the slinky is likely not at complete rest, which I'm going to talk about in our next slide. So, why does the bottom travel upwards that we saw in that graph? So, a slinky is a spring, meaning that it oscillates. And so when the slinky was dropped, it's very likely that the bottom of the slinky was oscillating upwards, which accounts for that upward movement of the graph. So what happens if we attach a mass to the bottom? Because that doesn't affect the relationship between the tension and the gravitational force, meaning they're still equal to each other, we're going to see the same exact thing, except that our force, whenever it starts to go down, will be greater because it has a higher mass.